Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of helical gear and design of helical gear. In the first lecture of this module, we studied about the helical gears, how it is different than the spur gear, and its different nomenclatures, because the gear tooth looks differently when we see it along the normal plane and along the tangential plane, and therefore the nomenclatures are related to the normal plane and the tangential plane. So there will be a pressure angle in the normal plane phi n, the pressure angle in the tangential plane phi t, and in addition the module will also be different in the tangential plane and the normal plane. So along the normal plane, the size of the tooth will be different, and so the module will be given by Mn, and in the transverse plane the size of the tooth will be another, and so the module in that plane will be Mt or simply M, and correspondingly there will be the circular pitch in the transverse direction P, T, and in the normal direction Pn, and the gear tooth was inclined by an angle psi which was called the helix angle. So in the first class we also studied about the forces which acts on a helical gear when force is transferred from driving gear to the driven gear, and we found that in this case one additional force acts in the axial direction, and therefore the normal force which is transmitted from driving gear to driven gear has three components. The first, which is useful component, is the tangential component Wt, and a component along the radial direction which acts along the axis of rotation is the Wr, and the component along the axial direction is Wa. So those forces we studied in our previous class, and the forces are given by Wr, which radially acts on a gear tooth, Wa, which acts in the direction of axis Wa, and this W is the normal force Wn, which acts in a plane. If the nomenclatures are given similar to the previous class, then this was taken as A, B, C, D, and thereafter E, F, G, H. So the normal force is acting along a plane E, G, B, E, G, B, C, and again E. Okay, that plane is this one, E, G, B, C, and E. Wn is acting in this way, Wn, and this angle is the normal pressure angle phi n. This is the pressure angle when the gear tooth is viewed in the normal plane. Now this Cb is the radial direction, and so the component of Wn in this Cb direction is your Wr, and the component of Wn in the GB direction is actually the bending load, and that is the Wn cos of the phi n. This Wn cos of the phi n is acting along G to B. So, now if the plane ABHG is taken, AB and HG. So, we have a force along GB, and the magnitude of that force is Wn cos of the phi n. Okay. And the angle ABG is the helix angle psi. So, this angle is psi. Now, we know that AB is the tangential direction. So, the component of this Wn cos phi n in the tangential direction AB will give the value of Wt, and that is Wn cos phi n and cos of the psi. And along the HB, the component of this Wn cos phi n, HB, along the HB is the axial direction. It is along the axis of rotation and along the z direction. This is the z direction, isn't it? So, along the axial direction you will get Wa, and its value is Wn cos of the phi n and sine of the psi, which is given here. Now, in this equation, Wn is a unknown, and the term Wt is known because the power which you want to transmit and the pinion diameter is dp, and the RPM of the pinion is np. So, from that we get the value of Wt, the transmitted load. So, this Wn is obtained in terms of Wt. So, this is Wn is Wt divided by cos phi n divided by cos psi, and then substituting Wn in the equation of Wr and Wa, we get radial force and axial force in terms of Wt and other known terms, the tangential pressure angle and the helix angle. Now, let us see one example. In this example, we have a motor bearing at A and B, and the center line of the bearings is at a distance of 250 mm, and on the shaft of the motor one helical gear is mounted, okay, and this is mounted in a cantilever way, and this pinion, helical pinion, is meshed with a helical gear, and this gear is mounted on a shaft with bearings this and this, okay. Now, the question is to determine reaction at the bearing A and B, and to find the forces which are transferred between the gear and the pinion is the question. In a figure, a 750 watt, the motor power is given 750 watt. So, H is 750 watt. An electric motor runs at 1800 RPM, and that will be the RPM of the pinion, because pinion is mounted on the motor. So, the RPM of the pinion is 1800 RPM. It is rotating in a clockwise direction as viewed from the positive x-axis. So, when the positive x-axis it is viewed, it is rotating in a clockwise direction, that is shown by this arrow. Key to the motor shaft is an 18-tooth helical pinion having a normal pressure angle of 20 degree. So, number of teeth on the pinion ZP is 18, and the normal pressure angle, this phi n, is 20 degree, and the helix angle psi is 30 degree, and a normal module of 3 mm. Mn normal module is given by 3 mm. The hand of the helix is shown in the figure. Make a 3-dimensional sketch of the motor shaft and pinion and show the forces acting on the pinion and the bearing reactions at A and B. The thrust should be taken out by A. Now, as the power is transmitted with the help of helical gear, and we know that in the helical gear system an axial load will also be there, and so on this shaft of the motor, the axial force will be exerted by the gear mechanism. So, among the bearing A and B, one of the bearings should take the thrust load. So, it is said that the thrust should be taken by A. So, A will take the thrust load. So, when you will take the reaction, when you will draw the free body diagram of this shaft, then at A there is a support, at B there is a support, and A is taking care of the thrust load, and so at the A there will be reaction in the x direction. So, with the coordinate system x, y and z perpendicular to the screen, you will have reaction R A in the x direction here, but there will not be a reaction in the x direction at B. Okay. And this is the point of contact which will be at a distance of half of the pitch diameter of the pinion, dp divided by 2. So, at this distance, at a distance of dp divided by 2, your load will act, or the forces will act, which will be transmitted from gear to the pinion. Okay, from gear to the pinion, and pinion is the driving gear, and it is rotating in a clockwise direction. Now, when you will draw the side view, it will look like this. This is the pinion and this one is the gear. Okay, the gear is drawn smaller, and when it is viewed from x-axis, positive x-axis, which is perpendicular to this screen in this figure, because this is your y-axis and z-axis is this one. This is the z-axis, y-axis and x-axis is perpendicular. This is rotating in a clockwise direction, and this is the driving gear. So, the transmitted load on the driving gear acts opposite to the direction of its rotation. So, transmitted load will act in this way. Okay, Wt on the pinion will act in this direction, and the radial load on the pinion will act towards its center. Okay, so Wr pinion will act in this way, and the axial force will act as per the hand of this gear. Okay, hand of the gear is given as, the bearing reaction is this one. The hand of the helix is shown in the figure. In the figure, the hand of the helix is not shown. Let it is the right hand. This is the left hand. So, in the right hand, the direction of axial load is determined from the right hand thumb rule. Make your fingers other than thumb of the right hand in the direction of rotation. Then the thumb will give you direction in which the axial load will act. So, when we are putting our fingers other than thumb of the right hand, then the thumb is towards the negative axis of the x, negative direction of the x. So, your WAX, WA of the pinion will act in the negative x direction. Okay. WTP is acting in the positive z direction, WRP is acting in the negative y direction, and this is acting in this way. So, at this point, which is the pitch point, you can show the forces which are acting here, and here you can show the reaction at B. The reaction is RPY, this is the y direction, and along the z direction there will be some reaction. So, along the z direction, let us take the RBZ, and this is RAY, and there will be RAZ. One will be in opposite direction. Let us see in our next figure. So, before that, the different other terms are obtained. So, pressure angle along the tangential direction is determined from the relation tan inverse tan of the phi n divided by cos psi, and that comes to this one. Similarly, the transverse module is determined knowing the normal module and the helix angle, that comes as 3.46 mm. So, therefore, pitch diameter of the pinion is dP, which is given by number of teeth on it multiplied by the transverse module 3.46, and so dP is 62.3, and the pitch point of the gears P is at a distance of dP divided by 2. Okay. The pitch line velocity is pi dn, where n is in RPS, and d is the pitch diameter we have determined here. So, it comes as this one, or in meter per second 5.87. So, knowing this pitch line velocity, we will have power which you want to transmit is equal to power which you are transmitting in terms of pitch line velocity and the your WT. Okay. Let us see the diagram. This is the diagram which is showing the reactions at the bearing B, reactions at the bearing A, and at the pitch point which is at a distance of dP divided by 2 from the axis, the forces which are transmitted. This is the WR, this is your WA, which is acting in the negative x direction, and WT, which is acting in the direction of z. Okay. So, let us see what we have determined. Z, WT is acting in the positive z, WR is negative y, and WA in the negative x direction. So, that is shown here, WA is in negative x direction, and the reactions are taken as FBZ, FBY. This B is not taking the thrust load, and there is no reaction in the direction of axis. This A bearing is taking the thrust load, and so in the direction of x there is a reactionary force, and the other reactionary force are given here, FAZ and FAY. Now, after drawing all these forces, our job is very simple. What we have to do is, we will apply the static equilibrium equation, that is summation of all forces in the direction of x should be 0, summation of all forces in the direction of z is equal to 0, summation of all forces in the direction of y is equal to 0, and number of unknowns are 1, 2, 3, 4, 5, and this torque T 6. So, 6 equations are required, but one of the unknown you can directly find from the forces shown in this figure. In the direction of x, there are only this force and this force. Therefore, directly you can say that Fa x is equal to Wa. Okay. So, one of the unknown is now known. So, number of unknowns are 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. Two equations are this one. First equation we have already used. Other three equations will be summation of movement along the direction of x, about x axis should be 0, summation of movement about any other axis we will take as equal to 0. So, we will have these equations and we will easily get the unknowns, and that is done here. First of all, Wt is determined knowing the power which you are transmitting from the motor, from motor to the pinion, from pinion to the gear, it is 750 watt, and pitch line velocity we have determined. So, the transmitted force is this one. From transmitted force, knowing the value of phi t and psi, you will get the Wr and Wa, and the normal load this one. So, just apply that and get the reactions. The summation of all forces has been done. So, taking moment about z axis, that is summation of movement about z is equal to 0 is providing this equation, and in this equation we have only one unknown, and that is obtained, Fby is equal to this one. Now, summing the forces along y gives us Fay is equal to this one. Taking moment about y axis, that is summation of movement about y is equal to 0 gives us the value of Fbz. Summing forces in the z direction, that means summation of all forces in the z direction is equal to 0 gives us Faz is equal to 38 Newton. Also, the torque T is Wt dP divided by 2, because this torque we are getting due to this transmitted force, and the transmitted force is acting at a distance of dP divided by 2. So, this T will equal to Wt multiplied by dP divided by 2. So, that is obtained, which is 3982 Newton mm. Now, for comparison, you can solve this problem by vector method also. In the vector method, the W vector, the forces which are acting at the pitch point of contact of the gear, can be written in this form. This is the Wa, this is your in the j direction Wr is acting. So, this is Wr, and in the z direction the transmitted load is acting, and this is 128. So, you are writing all the terms in terms of the vector. So, forces acting at a pitch point is represented by a vector given by this one. Okay. And other vectors are taken. The position vector capital B and capital C from origin capital A are capital RB and capital RC. Well, so and then by vectorical summation and taking moment, the same values of forces are obtained, reactionary forces are obtained. Now, the next thing which we will study is the stresses in helical gear. Similar to the spur gear, there are two modes of failure. Fatigue fracture due to fluctuating bending stresses at the root of the tooth, the surface fatigue, that means pitting of the tooth surfaces. And materials do not exhibit an endurance limit for repeated surface contact stresses. This is the problem. The bending stress number as per AGMA standard, this one is a similar form as for the case of spur gear, with the same correction factors. J is the geometry factor, Ko is the overload factor, Ks is the size factor, Km is the load distribution factor, Kb is the rim thickness factor, Kv is the dynamic factor or the velocity factor. Okay. So, the only difference will be in the determination of this geometry factor that we are going to study. This accounts for shape of tooth in bending stress equation. It includes a modification of Lewis form factor Y, fatigue stress concentration factor Kf, and the tooth load sharing ratio Mn. In the case of spur gear, we have found that the Mn was taken as 1. But for the case of helical gear, this will not be 1, but it will be equal to Pn divided by 0.95 Z, where Z is also called LAB, where LAB is the length of contact along the line of action. Small a is the point of engagement and small b is the end of engagement. So, along the line of action, the length of the line from A to B is called the LAB, or it is also represented by Z. So, values of Y and Z, this Y and Z are found in the AGMA standards. For helical gears with 20-degree normal pressure angle, use figure given in the coming slide to determine the value of J. This is the, it's not the spur gear, this is the helical gear. Helical gear geometry factor J, this is not actually J, but is the geometry factor J dash, and this is valid for a particular case, that is, this is valid for this one. Okay. The helix angle is corresponding to the helix angle, and corresponding to number of teeth, you will get the geometry factor J dash, and this is valid only for when the mating teeth is 75. If it is other than 75, then this is not valid. And so, to get the geometry factor for rest of the gears, we apply a modifying factor. So, J dash is obtained from the previous figure, which assumes the mating gear has 75 teeth. Get multiplier from the figure given below for the mating gear other than 75 teeth. Then obtain J as equal to J dash multiplied by the modifying factor. J dash modifying factor. Okay. Now, if you see this J dash modifying factor, then for 75 number of teeth, this is the number of teeth in mating gear element. So, if in the mating gear number of teeth is 75, then modifying factor is 1. So, for that case J will equal to J dash, but for other cases you will have some modifying factor, and your J dash obtained from the previous figure should be multiplied by modifying factor to get the value of J. This is the difference from the spur gear. Now, the load distribution factor, it is again this Cm is used for the surface fatigue and Km when we are studying the bending fatigue, Km. So, Km is obtained similar to the spur gear, that means depending on the source of power and depending on the face width, we get the value of Km. So, for accurate mounting, small bearing clearance, minimum deflection, precision gears, that means everything is very good. So, for that case, the corresponding to the face width, length of the face width, we get the value of Km or Cm. Now, if the gears are not so much precise, that means less rigid mounting is there, less accurate gears are there, contact across full face is lesser, then in that case the Km will be taken by this depending on the length of the face width. Now, if the gear is very accurate, then there is a chance of uniform distribution of load along its face width. So, if this is the face width, then all along the face width there will be uniform distribution of load, okay, this way. If it is not accurate, then there is no uniform distribution of load, and that we will take account of by multiplying the WT by the transmitted load by the mounting factor or the load distribution factor Km. So, we are just increasing the transmitted load by multiplying it by Km, because all these are greater than 1. Now, similar to the spur gear, this Km can also be obtained from the empirical relation given here. The Cm is obtained from this formula, and there are formulas to get the value of Cmc, Cpf, Cpm, Cma and Ce, which are given in the coming slides. This Cmc is obtained from this way for uncrowned teeth and crowned teeth. Uncrowned teeth means the face width is flat. Crowned means it is curved like this. Gear tooth is this one, okay, a curved is there, crowning is there for better engagement. For some cases it is done. For crowning, Cmc is 0.8 and the Cpf is obtained from this these three formulas depending on the value of face width f. It means this mounting factor or the load distribution factor depends on the face width, and it also depends on how the teeth are, whether it is crowned, uncrowned, and some other factors we will see. So, depending on the face width, if it is less than or equal to 25.4, this formula. If it is greater than or equal to 25.4 but less than or equal to 425 mm, then this formula. If it is in the range of 425 and less than or equal to 1000 mm, then this formula. Now, note that the values of f divided by 10 dp, dp is the pinion diameter, less than 0.05, we will take f divided by 10 dp equal to 0.05. Okay. So, if the value of this is less than 0.05, then also we take f divided by 10 dp as 0.05. Now, the other factors Cpm of the Km is equal to 1 and 1.1 depending on the straddle mounted. Straddle mounted means the shaft is supported like a simply supported beam. Here is the simply supported beam and the gear is mounted here. So, the radial load is acting at a distance of S1 from the mid plane, and the mid plane is at a distance of S divided by 2 and S divided by 2 from both the bearings, and the total span of the shaft or the distance of the bearings is S. So, depending on the ratio S1 divided by S, we will choose the value of Cpm, and Ce is again 0.8 and 1 depending on these values. The Cma is obtained from this formula, and constants A, B and C are obtained from this table. The dynamic factor is similar to the dynamic factor of spur gear, and it is obtained depending on the pitch line velocity of the gear and the way it is made. If it is made by cast iron and casting and the cast profile, then we will use this one. It is also called the Bath equation. And cut or milled profile, then this one. Hobbed and shaved profile, this one. Shaved and grout profile, this one. Shaved and grout means this is the precision gear. the surface finish is good. But when we are moving in this way, the surface finish is not good, and so this pitch line velocity should be smaller for this case, because there will be a value of Kb will be bigger. Now, the velocity factor or the dynamic factor may also be obtained knowing the quality value of the gear, how much quality gear is, whether it is a precision gear or it is not a precision gear. Then knowing the value of QV, we can get the value of this B, and knowing the B we will get the value of A, and then substituting A and B we will get the value of Kv, where V is the pitch line velocity in meter per second, and this QV depends on how the gear is made. So, the quality number 3 to 7 will include most commercial quality gears, quality number 8 to 12 are of precision qualities. Well, so you see this one from this figure, also you can get the value of the Kv knowing the quality value of the gear or the quality number of the gear, knowing the pitch line velocity in meter per second. Now, the maximum value of pitch line velocity up to any curve can be used is obtained from this one. So, for any quality you want to know what should be the maximum pitch line velocity where a particular curve is applicable. Substitute this QV in this equation, you will get the VET, and that will be VET for that particular quality. Okay. So, gears in typical machine design would fall into the classes represented by curves 5, 6, 7, which are for the gears made by hobbing or shaping with average to good tooling. If the teeth are finish ground and shaped, it means surface finish is very good. To improve the accuracy of the tooth profile and spacing, curves 8, 9, 10, 11 should be used. Under very special conditions where teeth of high precision are used, in applications where there is little chance of developing external dynamic loads, the shaded area can be used. And in the shaded area, you may see that the value of Kv is very much near to 1, and so the transmitted load will be equal to the actual transmitted load multiplied by a very small quantity, and so this W will be increased by a small value. Then the idler factor, similar to the spur gear, the idler's effect is there because idler is subjected to two-way loading. There will be load in this direction and load in this direction. So, two-way loading is there. It means when a gear tooth is at this location, then it is subjected to load along this way, and when it is coming to this way, then it is subjected to load in this direction. Okay. So, two-way loading will be there like this, completely reverse load. In the case of pinion and gear, the load will be represented by this with amplitude of the bending moment is smaller in comparison to the idler, where the amplitude of load is given by this one, and here the mean load is 0. So, the type and amount of load which is acting on the idler is very much different in comparison to the gear and pinion, and so that should be taken into account by the idler factor. On an idler, the value of Ki will be 1.42. So, W will be Wt, the transmitted load, multiplied by 1.42. It means 42% increase in Wt you are making for the case of idler. Now, in addition to bending, on the helical gear also, the surface stresses acts due to the contact stresses at the point of contact, And we have found during study of forces on the spur gear that the maximum contact stress occurs when the contact is along the pitch point. And the contact stresses was determined by an analogy of cylinders under contact. And we have found by this analogy the Hertzian contact stress, and the Hertzian contact stress on a gear is given by Wt F dP. dP is the pinion pitch diameter, and nu P is the Poisson's ratio for the pinion, and nu G is the Poisson's ratio for the gear. EP is the Young's modulus for the pinion, and EG is the Young's modulus for the gear, and cos phi, and this is actually phi t and phi t. Transverse pressure angle mg divided by mg plus 1, where mg is given by number of teeth on the gear divided by number of teeth on the pinion. Well, so this equation is converted into a smaller form by taking this term, under root of this term, taking as a Cp, the elastic coefficient, and this term as geometry factor for pitting resistance I. So those are given here. Cp is this one, and the Cp is determined from this table depending on the material of the pinion, depending on the material of the gear. If the material of the pinion is cast iron and material of the gear is steel, then Cp, the elastic constant, is 166 megapascal to the power 0.5. Otherwise, if you know the elastic properties of the material of gear and pinion, you can find the value of Cp using this formula. So, this term is taken as the geometry factor for the pitting resistance, which is given by this I, and this here we have mg plus 1 for the external gear and mg minus 1 for the internal gear. For the spur gear, this mn was 1, but for the helical gear this will be not 1. We have to determine the value of mn. So, for the case of helical gear, the mn is given by P capital N, this is not the normal pitch, it is something else, divided by 0.95 Z. Z is the line of contact or the length of contact LAB, and the Pn is given by normal pitch of the helical gear multiplied by cos of the normal pressure angle, and LAB or Z is given by within the bracket Rp, pitch circle radius, plus addendum, length of the addendum, plus whole square, minus R, base circle diameter of the pinion square, bracket close, and it to the power half. Similarly, the second bracket term is R of the gear, pitch circle radius of the gear, plus addendum. Addendum will be same for pinion and the gear, minus RBG, base circle radius of the gear square, and whole to the power half, minus pitch circle radius of the pinion plus pitch circle radius of the gear multiplied by sine of the phi t, where phi t is the transverse pressure angle, and the base circle radius is given by R cos phi t, where R is the pitch circle radius. So, knowing the value of Cp and I, the surface stress will equal to this formula. Now, AGMA has multiplied this formula to different factors to get the effect of velocity, effect of overload, effect of mounting errors, and the effect of size to get the surface fatigue stress on the gear when they are in contact. So, from this formula you will get the value of sigma c, and from the earlier formula we get the value of sigma b, the bending fatigue stress. So, we have obtained what bending stress will act on a helical gear and what the contact stresses will act, or the Hertzian contact stress will act on the helical gear which are in mesh. After that we will find the bending fatigue strength, that means SFB dash, from the literature. From the literature means from the data book. From the data book, for different materials the value of SFB dash are given, and this is given for life equal to 1 into 10 to the power 7 cycles, reliability given by 0.99, and temperature room temperature. So, we have to modify it depending on our requirement, and so we will get SFB. Similarly, from the literature we will get the surface fatigue strength, that is SFC dash, and it will be modified to as per our requirement, as per our life requirement, as per our reliability requirement and the temperature requirement and others. So, let us see quickly about that. So, the SFC is given by this, the AGMA surface fatigue strength for gear material. These are the correction factors. This is the life correction factor, hardness ratio correction factor, temperature factor and the reliability factor. These factors are obtained from the literature. These type of table or the graphs are there. From that you will get the value of SFC dash and also SFB dash. The correction factors are there for the life correction factor, the hardness ratio correction factor CH. Depending on the hardness of the pinion and the hardness of the gear, you will get the ratio, and depending on the value of this ratio you will have different values of the A, and these A is substituted here to get the value of CH, or for the surface fatigue strength KH. From this figure also you can get the value of hardness ratio factor. For a single reduction gear ratio mg, depending on the value of mg, that means ratio of zg, number of teeth on the gear to number of teeth of the pinion, you will have this one, and depending on calculated hardness ratio h, brinell hardness of the pinion and brinell hardness of the gear, you will select a particular curve and you will get the value of CH. Now, when HBP divided by HBG is less than 1.2, that means if this ratio is below this one, then what to do, because there is no any curve. So, for that use CH is equal to 1. Hardness ratio factor, knowing the surface finish of the pinion FP, micro inches RA, you will have these curves. So, depending on the brinell hardness of the gear HBG, you will get the hardness ratio factor CH. Okay. Now, the reliability factor KR or CR, both are same. This accounts for statistical distribution of material fatigue failures, does not account for load variation. Since reliability is highly non-linear, if interpolation between table values is needed, use the least square regression fit. The value of KR, depending on the range of reliability you want, if the reliability you want is greater than 50% but less than 0.99, then this is the formula. If the reliability is greater than or equal to 0.99 but less than or equal to 0.9999, then you have to use this formula, or you can use this one also, to this table value also, to get the value of KR or the CR. In this you see, for 99% reliability, the reliability factor is 1, because the strengths SFB dash and SFC dash are corresponding to reliability equal to 99, and so for that it is 1. But if you want reliability more than this, then this Kr is bigger value. Why? Because you see Cr or Kr is in the here. So if it is more, then what it will do is it will reduce this value. If it is lesser, then it will increase the value. So that is shown here, okay, like that. Then selection of material based on contact stress. What we have to do actually is in the same spur gear, we have determined sigma b, the bending stress which is acting, and the bending fatigue strength SFB. Applying all the corrections here, applying all the corrections here. Now sigma b should be less than SFB. Similarly, the contact stress sigma c or sigma h, the Hertzian stress, whatever the name you adopt, H is saying the Hertzian stress, Hertzian contact stress, or here simply C. This you have determined, and SFC you have determined. The surface fatigue strength you have determined. The value of this sigma C should be less than SFC. From these two, you will get the factor of safety guarding against bending fatigue, NF, and that is SFB, fully corrected bending fatigue strength divided by the bending stress which is acting, applying all the factors. Similarly, factor of safety guarding against the surface contact stresses or the surface fatigue is C, and that is SFC divided by sigma C. Now, knowing that this sigma C has a relationship with WT, non-linear WT, means sigma C is proportional to this one and sigma B is proportional to only WT. So, again we will make correction in it. We will say the factor of safety guarding against contact stresses is NC square of the SFC divided by sigma C, and thus both NF and NC are related to the transmitted load WT, okay, which is shown here. NF fully corrected bending strength divided by bending stress, and NS fully corrected contact stress divided by contact stress imposed square. Now, this exponent will be 3 for crowned teeth. With the definition of equation C, compare NF, factor of safety guarding against fatigue, with factor identify the threat to loss of function with confidence. So, these are the references which were used in the chapter of helical gear. Gears are designed very much similar to the spur gear. The only difference is determination of geometry factor, and in the geometry factor for pitting resistance. Thank you.
and I teach sociology at IIT Kanpur. I'm a bit about how we can think about globalization. Now, one of the important concepts in and particularly global studies is that of global flows, developed by the sociologist and he said that as the world is becoming a more, you increasingly see the movement of different both tangible and non-tangible across to begin at how your day proceeds. I often need my day. Now, if you think about it, something that is that originated in actually a drink that comes to us from quite far away. So, and this is something that has happened not immediately, happened 400 or 500 years ago. This kind of movement actually happened now, this kind of movement of people and goods flows that Apadura talks about. A second category, financial flows, and a is the kind of volatility that you can see in economy. For instance, in 2008, experienced a very serious economic jolt. Developments in the country of Iceland had across many countries in the world. Of the kind of financial flows that so we're not only talking about money flowing from place to place, decisions made in one place having parts of the world. Apadure also argues that there is a which he refers to as the flow of images. This is something that I'm sure you're quite used to. Watch on television today, for instance, you may actually be channels that have originated elsewhere. More than that, it could also be today is influenced by shows abroad. Similarly, you can have content that was which makes its way to other places in the world. Hollywood films are extremely popular in many countries. So this kind of movement of media is be an important part of globalization. He talks about is the movement of ideas. So this means that ideas that are popular in one part of the world are not restricted to that part alone, but they actually travel across borders. So for instance, something that you may read about in the papers would be, say, events such as gay pride events. Now, gay pride events have their origin in places like New York. But the idea that there should be equality between people, irrespective of what their sexual preference is, that is an idea that has now become popular across the world. And so that's the fourth category of flows that he referred to. The fifth category of flows that Appadurai talks about is that of technology. An easy way to think about this is, let's say tomorrow there is news announced that Apple is going to release iPhone 7. As you can anticipate, there is going to be a lot of excitement in many parts of the world, and people are going to start queuing up, waiting for those products to actually come to their country. So, technology is something that is quite exciting and really moves across various national borders.